So now that we've explained the theory, comes the difficult part, of course. How can we prove this theory? It sounds very nice, but what proof do we have to say that this is actually what's happening? Well, firstly, everything is according to the laws of physics. We've looked at every single theory out there, and every single theory has flaws, things against the laws of physics. But this theory is self-explanatory. It makes sense. But we need to prove it. So, after thinking long and hard of how we can actually come up with some predictions and see if those predictions come true or not, we came up with 3 predictions. The first prediction: as we move further away from the ground, gravity gets weaker, as we explained in this explanation. And the prediction, we predicted that at an altitude where gravity is exactly half of the gravity at sea level, in other words, 4.9 meters per second squared. So our prediction is, if the ground level, if the earth was that big, that on the ground of the earth gravity was half, we predicted that the surface area of the big earth should be exactly double. Why? Because if space, the fabric of space, is coming down, the further away you are from the center, the bigger the planet becomes, or the bigger the sphere becomes. So our first prediction was, at the altitude where gravity is exactly half, the surface area of the bigger sphere should be, the surface area should have exactly double the surface area of the earth. So that was the first prediction. Second prediction, we predict that gravitational time dilation and normal time dilation due to speed are one and the exact same. So what is gravitational time dilation? Gravitational time dilation is, on the earth, time runs slower as opposed to in distant space. So our prediction was that this slowness in time is due to time dilation due to speed gravitational time dilation and time dilation due to speed are the same thing, they're not separate things. And the third prediction we made was that if you send a signal from the International Space Station to the ground, and from the ground to the space station at the same time, and the difference between the space station and the ground is 400 kilometers, our prediction is that the two signals will have a difference in time. And the time difference between the two signals should be approximately 120 nanoseconds between the two signals, meaning the signal going from the Earth to the space station will be slower, and the signal coming from the space station to the Earth will be slightly faster, and the difference between them two will be 120 nanoseconds. So, the first prediction. The further you go from the Earth, this is the Earth, and the gravity is 9.8 meters per second squared. Actually, so at ground level, the gravity is 9.8 meters per second squared, and where gravity becomes exactly half, the altitude is 2,649 kilometers above sea level. So we predict that if the Earth was this size, then the surface area of the new Earth should be exactly double. So we did the maths, and the Earth is 6,371 kilometers. The radius of the Earth is 6,371 kilometers. And the altitude where gravity becomes exactly half is 2,649 kilometers. So if you add these two up, you get 9,020 kilometers. So our theory says that if you have a sphere or a planet with the same mass as the Earth, or the Earth became bigger, and the radius was 9,020 kilometers, then the surface area should be exactly double. So let's calculate that. So what's the surface area of the Earth? So the surface area of the Earth works out to 510 million square kilometers. The surface area of the Earth is 510 million square kilometers, and the surface area of the big Earth, or a big sphere with a radius of 9,020 kilometers, that's where gravity is exactly 50%, and it works out to exactly double. This is the surface area of the big Earth, and this is the surface area of the Earth. At 50% gravity, the surface area is exactly double. Why it should be exactly double? Why? And this would only happen if the vacuum space or the fabric of space was coming down towards the Earth. At a higher level, it would be slower. At a lower level, it would be faster. But the slower it gets, the surface area should exactly match the speed of its slowness and of its fastness. So this first prediction, this is the first prediction, and it comes out to exactly how it's been predicted. The other thing we realize is, if gravity was a particle-based force, these figures wouldn't be like they are, because the way particle forces work is like the electromagnetic force. Photons are emitted from the south, and they go back to the north, and they will go back in a complete circle. They will go right round the Earth and back, and the same particles will go around and keep on going around, and this is what the electromagnetic force is. So these figures would never match this model, and because the particles are going back, the effect of electromagnetic force is limited, and the effect of gravity is unlimited. So a particle force could never be unlimited because of the fact that the particle has to come back. So this tells us that it can't be a particle force. The other way we know that Albert Einstein has to be correct, that gravity is not a force, is a black hole. Now, you have a black hole, and you have its event horizon. Now, nothing can come out of the black hole, regardless of what it is. Nothing can come out of a black hole. So if it was a particle force, like the electromagnetic force, like the strong force, like the weak nuclear force, then you would need particles to be emitted and particles to go back. The black hole can't emit particles. No particles can come out of the black hole. Things can go And if it was a particle force, then there would be no gravity associated with a black hole, because there's no particle to pull anything inside. But the black hole has large amounts of gravity. But we know for certain that particles are not creating the force. Particles are not creating the gravity associated with a black hole, because no particles can be emitted. So the evidence against particles being the force are mounting up, and we're seeing that it has to be something, but it can't be a particle force. So our second prediction is that gravitational time dilation and time dilation due to speed of travel are the same thing. So what speed would you have to be at to slow down to the same level as the level on the Earth? So we need to find out what is the gravitational time dilation of the Earth. And we find out it works out to 2 seconds for every 100 years. So we need to find out at what speed a person would need to travel at to slow down at the rate of 2 seconds for 100 years. And it works out that if you are traveling at 11.3 kilometers per second, so 11.3 kilometers per second. If you are going at 11.3 kilometers per second, your time will slow down by 2 seconds for every 100 years, same as the Earth. So this was a huge disappointment for us. We had estimated it to be something like 14.5 kilometers per second. So we looked at the figures again and again, and suddenly the penny dropped. The escape velocity of the Earth is 11.2 kilometers per second. The escape velocity of the Earth is the escape velocity of the Earth is 11.2 kilometers per second, and our calculations that the fabric of space is moving down at 11.3 kilometers per second, an almost perfect match. And this cannot just be a coincidence that our calculations tell us that time dilation is when you travel at 11.2 kilometers per second, and the escape velocity of the Earth is also 11.2 kilometers per second. So that means that the two are exactly matching. And this tells us that gravitational time dilation is due to the vacuum space coming down at 11.2 kilometers per second. So that's two predictions that are exact matches. The first one was at half gravity, the altitude at half gravity, the area should be exactly double the Earth, and it came to exactly double. And the second prediction was that gravitational time dilation and time dilation due to speed are the same thing, and we calculate what speed space would have to come down to match the time dilation of the Earth, and it works out that that figure is exactly the same as the escape velocity. So that's two predictions that are bang on, and they have no reason to be bang on unless the theory is correct. So the third prediction, that a signal from the International Space Center and the ground was to be emitted at the same time, the signal from the ground going to the space station should be 120 nanoseconds slower than the signal coming from the space station to the ground. Unfortunately, we have not been able to carry out this experiment, and this is one of the reasons why this video was made, is to help us, or to find someone who can help us to carry out these experiments. So you might have noticed that the solutions to the different scientific problems that we predicted, most of them have been explained, but a few have been left out for another video. And we hope you enjoyed the video, and we hope you found it as fascinating as we have found it fascinating, and we hope that you can see the potential in this theory for new science and new discoveries in the field of the vacuum energy and the explanation for gravity. So on that note, we bid you goodbye, and we will see you next time we make another video. Thank you.